Welcome to the Explainer. Today, we're unpacking something that sits at the absolute foundation of modern software, yet it almost always remains completely out of sight. We are prying open the black box of database storage engines. If you've ever wondered how databases actually store and retrieve data under the hood, you are in the exact right place. We're going to break down the brilliant engineering architectures that power everything from your everyday mobile apps all the way up to massive planetary-scale business analytics.
Okay, let's dive right into this. I mean, think about it. What actually happens when you hit save? Imagine the sheer volume of operations happening totally behind the scenes every single time a system writes or reads data. When an application pulls up a user profile, there's this intense mechanical and algorithmic dance taking place on a server somewhere. And what's really fascinating is that this dance is entirely governed by trade-offs. The engineers who built these systems had to make incredibly difficult choices. What do you prioritize? Speed of writing, speed of reading, storage space? Well, let's look at where it all begins.
Believe it or not, this right here is arguably the world's simplest database. It's literally just 2 lines of a bash script. The dbSet function simply appends a new key and value to the very end of a text file. And the dbGet function? It just uses basic command line tools like grep and tail to scan that file and find the most recent value for a key. Now, the write performance of this database is actually incredible because it just appends text to the end of a file. It's basically as fast a write operation as your hardware will allow, but it suffers from a fatal flaw. When you want to read data, it has a time complexity of O of n. That means it has to scan the entire file from top to bottom to find your record. If your database doubles in size, your search takes twice as long. Obviously, that is completely unscalable.
So, to fix our horribly slow read times, we have to introduce a new data structure, the index. An index is essentially just additional metadata kept on the side. Think of it exactly like the index at the back of a textbook. Instead of reading the whole book just to find one specific keyword, you look at the index, which acts as a signpost pointing you exactly to the page you need. But we have to frame this as what it truly is. It's a crucial engineering compromise.
So, the crucial point is that you cannot have perfect reads and perfect writes simultaneously. This is the eternal database trade-off. Well-chosen indexes absolutely speed up your read queries, making your application feel super snappy and responsive. But every single time you add an index, you are actively slowing down your writes. Why? Because whenever new data is written to the database, you don't just update the core data file. Every corresponding index has to be updated too. You are literally trading write speed for read speed. Let's look at one of the simplest, most elegant indexing strategies out there, the hash index, which is used by storage engines like Bitcask. The idea is brilliant but straightforward. You keep a hash map entirely in memory. Every time you append a new record to your data file on disk, you update this in-memory map so that the key points directly to the exact byte offset on the disk where that data lives. When you need to read a record, you check memory, get the offset, and make a single, lightning-fast disk seek. It gives you incredible performance for both reads and writes. But there is a massive limitation here. All of your keys must fit into your available RAM. Plus, because we're constantly appending to our disk file to get those fast writes, we're eventually going to run out of disk space completely. So how do modern databases solve that disk space issue while keeping those crazy fast append-only writes? They use a remarkably clever background process called compaction. First, the database breaks the continuous log into smaller, manageable segments. Then, a background process looks at these segments and throws away any duplicate keys, keeping only the most recent update for each key. Finally, it merges these compacted segments together into a new, smaller file. The real brilliance here is that this all happens in a background thread. Your application just keeps reading and writing to the old segments without any interruption. And once the new compacted segment is ready, the system seamlessly switches over and trashes the old files. Which brings us to a huge evolution in storage, sorted string tables, or SSTables, which form the backbone of log-structured merge trees, or LSM-trees. Instead of just appending data in random order, what if we require the key-value pairs in our segments to be sorted by key? We do this by keeping incoming writes in a balanced, sorted tree in memory, often called a memtable. When that memtable gets big enough, we just flush it to disk as a brand new, pre-sorted SSTable file. Because the data's already sorted in memory, writing it to disk is incredibly fast and sequential. This architecture gives us the best of both worlds, blistering write speeds and highly efficient searches. But hey, the log-structured approach isn't the only game in town. Let's pivot to the competing philosophy that has absolutely dominated almost all relational databases for decades, the B-tree. Unlike LSM-trees, which append data to new files, a B-tree completely shifts the paradigm. It breaks the database down into fixed-size blocks, or pages, traditionally 4 kilobytes in size. It reads and writes one page at a time, and crucially, it updates data in place. It basically treats the disk like memory, using references, essentially on-disk pointers, to connect parent pages to child pages, forming this massive balanced tree.
The reason B-trees have stood the test of time really comes down to staggering mathematical efficiency, O of log n. Because the tree is perfectly balanced and each page contains hundreds of references to child pages, the depth of the tree stays remarkably shallow even as the database grows to massive, massive sizes. What does O of log n actually mean in practice? It means you might only need a tiny handful of page jumps, literally just 3 or 4 disk seeks, to find one specific key hidden among hundreds of millions of records. That is wild.
All right, so we've got 2 major schools of thought here. LSM trees rely on append-only sequential writes, making them absolute monsters for write-heavy workloads. B-trees, on the other hand, update data in place and generally offer highly predictable, consistently fast read performance. Now, because B-trees overwrite data directly, they have to rely on a write-ahead log, which is essentially a safe sequential scratchpad to protect data in case the server loses power before the page is safely written to disk. Just remember, there is no single perfect system in software engineering. There's only the right system for your specific workload. Now, brace yourself for a bit of a plot twist. Everything we just learned, LSM trees, B-trees, hash indexes, it's all perfectly engineered for everyday transaction processing. Looking up a user profile, adding an item to a cart, processing a quick payment. But what happens when your business analysts need to scan millions or even billions of historical records to figure out a macro-level market trend? If they run that massive query on your standard B-tree, it's going to scan so many pages that it might lock up the entire system and literally crash your customer-facing website.
And this brilliantly illustrates the grand divide in the database world. On one side, we have OLTP, online transaction processing. This is your app's operational database, built for small, incredibly fast, user-facing queries that look up data by a specific key. On the exact opposite side, we have OLAP, online analytic processing. These are the systems built for business intelligence, designed from the ground up to execute massive bulk scans and complex aggregations over petabytes of data. Because these 2 workloads are basically at war with each other, modern companies don't even try to mix them. Instead, they build entirely separate databases called data warehouses. A data warehouse is a massive, read-only copy of the data pulled from all the various OLTP systems across the company. The data is extracted, transformed, and loaded, a process you've probably heard of called ETL, into this isolated environment. This lets business analysts run their heaviest, most aggressive queries without ever putting the main operational databases at risk. Inside these data warehouses, the data is usually organized totally differently, often using what's called a star schema. Right in the center, you have a massive fact table, which logs every single individual event, like, say, every item ever scanned at a cash register over the last 5 years. Radiating outward from that fact table are dimension tables, which hold all the metadata answering the who, what, where, and when of those events. Because we want to capture every possible detail for later analysis, these fact tables can easily get incredibly bloated, sometimes exceeding 100 columns in width.
But that extreme width brings us to a really critical realization. When a business analyst writes a query to find out, say, total revenue by month, they might only care about 3 specific columns: the date, the product, and the price. They are completely ignoring the other 97 columns in that massive fact table. So we really have to ask ourselves, how can we optimize our database engine if we rarely ever need the entire row?
If you use a traditional row-oriented database for this, like the ones powering OLTP systems, it's a disaster. The data is stored sequentially by row on the disk. That means to calculate our analytics query, the storage engine is forced to load the entire row from the disk into memory, parse the whole thing, and then literally throw away most of the data because we don't need it. When you multiply that wasted effort across billions of rows, it creates a massive, system-choking bottleneck in reading from the hard drive, what engineers call disk I/O.
The fix for this in the OLAP world is absolutely brilliant: column-oriented storage. Instead of storing all the values from one row together, we completely flip the paradigm. We store all the values from each individual column together in their own separate files. If your query only needs the date and the quantity, the database engine only reads those two specific column files from the disk. It completely ignores the rest of the data. This results in a massive, game-changing reduction in the amount of data transferred from the disk to the CPU. Now, what's really fascinating here is how storing data this way naturally unlocks some insane compression techniques. Think about it. If you store a column of country codes, you're going to have massive sequences of identical repetitive values. We can use bitmap encoding, creating a simple string of ones and zeros indicating if a row matches a value. Then we can use run-length encoding to compress long sequences of repetitive zeros into just a few bytes. And because the data is packed so tightly, we can use vectorized processing. This is where modern CPUs can actually crunch huge chunks of this compressed data directly inside their ultra-fast internal memory without even uncompressing it first. So, to wrap up this explainer, I want to throw a challenge your way. Think about the architecture at your own company or in the side projects you're building. Are you trying to force a traditional B tree to do heavy analytics? Or maybe you're using a column store for something that requires rapid single record updates? Remember, as we've seen today, under the hood of every single database is a series of deliberate compromises. There is no such thing as the objectively best database engine. The best database entirely depends on the question you are trying to ask of your data. So what question are you asking?